Well, what we've done is we figured out what is the probability that any two numbers are compared. What we're left with doing is figuring out, is using that probability for all pairs of numbers. So if we're going to count the total number of comparisons, we want to calculate all of these xij's. So that's what's the probability that the first number is compared to every other number? What's the probability that the second number is compared to every other number? That the third number is compared to every other number, and so on. So we're going to look at all possible comparisons, and we're going to sum up those expected values for whether or not the comparison happened or not. Well, if we want the average, that's basically like saying the expected value. So the expected value for the total number of comparisons, because of the linearity of expectations, is just the expected value for each possible values of xij. Alright, so this is the equation we have. Well, what's the expected value for any random variable? Well, this is an indicator variable, so it's just one. So it's the probability that the comparison happened times 1 plus the probability the comparison didn't happen times 0. Well, you know, anything times 0 we can just get rid of. So all we need is this probability, and we know that probability. That probability is this, the probability that any two numbers get compared. So that's what we have. That's the expected number of comparisons on any call to Quicksort. Alright, so we want to look at this asymptotically. So we want to look at this average asymptotically, which means it doesn't really do us any good to plug in values for n here, because that's just going to give us a total number of comparisons for a specific value of n. We want to look at this in the more general case. So what I'm going to do is simplify this summation. Alright, so let's simplify it by first looking at the inner sum. So we're going to look at just this part. Let's look at it for a couple of specific values. So let's look at it for the smallest value of I and the largest, and another value of I. So if we plug in I is equal to 1 into this red part here, the inner summation, I'm going to plug in 1 here and 1 here. When I do that, my summation, the inner summation only, simplifies to this equation. And if you look at that, it's 2. I can just move the 2 outside the summation. It's 2 times 1/2 plus 1/3 plus all the way up to the upper bound, which is plugging an n in here. So it's 1 over n. That's just 1 over n. Because you got the plus 1 and the minus 1. So that's it. 2 times that series. Well, let's plug in another value for I. Let's just plug in 5 into here and here. Well, when you plug in 5, your bottom limit here becomes 6, and we end up with 2 over j minus 4. Well, again, the 2 can come out just like we did before, and we'll have 2 times, well, what is 1 over 6 minus 4? That's a half. What is 1 over 7 minus 4? That's a third, all the way up to 1 over n minus 5 plus 1. Well, if you notice, between these two equations, they share in common the 2, and they share in common these first terms. So you have to ask yourself which of these series has more values and which of these series is bigger. So which series is bigger? The one where we have I is equal to 1, or the one where we have I equal to 5? Well, that will be the top series here. The reason for that is this goes from 2 up to n, so it has more values in it, and each of the values sort of starts at a half and then just decreases in the same manner for each of them. So the fact that we have more values in this series means that when we have I is equal to 1, that's greater than any of the other times that we have this inner summation. So we have I equals 1, then when it becomes 2, this inner summation becomes less. When it becomes 3, this inner summation becomes less, and so on. So the inner summation is maximized with I equals 1. So what we can do is just plug in I equals 1 for that inner summation, and then we will have an inequality. So that gives us the maximum value for the inner summation, and it gets rid of I in several places, which means we can simplify our nested summations. Alright, so that inner summation, if you notice, no longer depends on I, which means I can, since it no longer depends on I, I could just multiply by the number of times that that summation occurs. So this outer summation occurs roughly n times. So it's like taking this inner summation and multiplying it by n. So that outer summation just becomes the multiplicative factor by n there. So now we have 2n times that inner summation. Alright, the next step is to turn this into an integral, just because that's going to be easier for us to evaluate than the summation in this particular case. So it turns out if you have the discrete summation, that's less than or equal to 2 to the n of 1 over x dx. And why is that? That's because of this particular series. If we have 1 over j, that's equal to a half. So when our first element here is at a half, and then our next element here that we would be summing is at a third, and so on. So we just continually are taking the sum of all those values. Well, when you take the integral, you're actually looking at something a little larger. So you can think of the discrete version as not including these little caps, and the integral as including these caps, which is why I have the inequality here when we change this from a discrete to an integral. Okay, well, this is a definite integral. It's a definite integral, so we can evaluate it, and 1 over x dx is nothing but the natural log of x. So we're going to evaluate this and have 2n times the natural log of n minus the natural log of 1. The natural log of 1 is 0. So we're left with 2n natural log of 1, and like we've seen in previous slides, you can do a change of base, which means that the average running time, when computed as the average number of comparisons that happen inside Quicksort, is big O of n log n. So that's our summary. The expected number of comparisons is big O of n log n, and the expected number of comparisons is directly proportional to the total running time of Quicksort. So the average asymptotic running time of Quicksort is big O of n log n.